Hi students, this is the 5th class of Electromagnetic Induction chapter. Today's class we can discuss about what is meant by induction and types. Okay, what is meant by induction and types of induction we can discuss. Already in Faraday's experiment we told that what will happen when the flux is going to be changes, EMF, electromotive force or current induces in a coil. This one is going to be produced as the current because of based on the deflection produced in the galvanometer. No? Same way, induction means the process of producing the current. The process of producing the current in a coil. Process of producing the current in a coil, due to changing magnetic flux, changing magnetic flux linked with it. It's called as what? Induction. Induction is the process of producing the current. Yes or no? Producing the current in a coil due to changing magnetic flux linked with it or linked with the coil. We are going to call it as what? Induction. There will be two types of induction. When you come to the types of induction, there will be two types. One is self-induction. Okay, the word itself is indicating self-induction. Second one is mutual induction. Self-induction and second one is mutual induction. Okay, these are the types of induction. So here, the process of producing the current in a coil due to changing magnetic flux linked with it, we are going to call it as what? Induction. There will be two types, self-induction, another will be mutual induction. Now today's class we can discuss about self-induction. Okay, now we can discuss about what? Self-induction. Self-induction. Okay, so here I have to explain the concept of self-induction means I am going to take one coil. This is the coil C. This coil C, I am going to connect it to a battery. This coil C, I am going to connect it to a battery with the help of rheostat. I am going to connect it to a battery with the help of rheostat. Okay. Here already people know that this is the coil. Okay, there will be an insulating wire wound in the form of N Anil. I am going to call this what? Coil. This coil I am going to connect it to a battery with the help of rheostat. Rheostat means already people know that variable resistance. This is a variable resistance. We can increase or decrease the resistance. Based on increasing and decreasing the resistance, we can vary the current in a circuit. Here, when the battery is connected to a coil, I am going to switch on the circuit. Or I am going to close the key. Here I am going to key. I am going to take the key. I am going to place the key. What will happen? The current will start flowing in the coil. Yes or no? When the current starts flowing in the coil. When the current will start flowing in the coil, what will happen? This coil is going to become magnet. When it is going to become magnet, it is going to produce the magnetic field lines. When the magnetic field lines is going to be produced by the coil, the same field lines are going to be cut by the coil. Yes or no? The same field lines are going to be cut by the coil. When the same field lines are going to be cut by the coil, flux is going to be changes. When the flux is going to be changes, the EMF is going to be induces. Yes, the EMF is going to be induces. That one we are going to call it as what? Self-induction. Means we are going to produce the EMF in a coil due to changing current in the same coil. We are going to call it as what? Self-induction. Yes, we are going to call it as what? Self-induction. Simple thing. I am going to take a coil. That coil is connected to a battery with the help of what? Rheostat. When the circuit is closed, the key is closed, what will happen? The current will start flowing in the coil. When the current starts flowing in the coil, what will happen? The coil is going to become magnet, means it is going to be produces the magnetic field lines. When it is going to be produces the magnetic field lines, what are the field lines are produced by the coil? They are going to be cut by the coil. What will happen? The flux is going to be changes. When the flux changes, the EMF is going to be induces. The EMF is going to be induces because of what? Variation of current in the same coil. We are going to call it as what? Self. In the same coil, we are going to induce the EMF, and by changing the current, both are in the same coil, we are going to call it as what? Self-induction. The definition we can write, what is meant by self-induction? We can define the process of inducing the EMF. The process of inducing the EMF, electromotive force. The process of inducing the EMF in a coil. The process of inducing in a coil due to changing current. Due to changing current in the same coil. Due to changing current in the same coil, we are going to call it as what? Self-induction. Clear? Yes, in this coil, we are going to produce the EMF by changing the current in the same coil. We are going to call it as what? Self-induction. Okay. Here, already we know what is meant by self-induction. Now we have to write the expression for induced EMF. Yes, the expression for induced EMF. Expression for induced EMF. Expression for induced EMF. Okay. We have to write the expression for induced EMF. Already here I told that when I am going to increase the current, what will happen? The flux is going to be changes. Means when we are going to increase the current, flux will changes, or decrease the current, the flux is going to be changes. Means the flux is directly proportional to, we can write current I. Know flux is directly proportional to current I. Here we have to remove the proportionality constant. That proportionality constant we are going to call it as coefficient of self-induction or self-inductance. Here, that what are the current we are going to change here? Here flux is going to be changes. When the current will be constant, there is no flux change. Clear? No? Yes or no? Means here we can write the flux change is directly proportional to what? Current. Here we have to remove the proportionality constant. This proportionality constant only we are going to call it as what? Coefficient of self-induction or self-inductance. Yes, the coefficient of self-induction or self-inductance. L is what? Coefficient of self-induction. Coefficient of self-induction coefficient of self-induction or self-inductance. 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 Now I have to write the expression for induced EMF. No? Yes, I have to write the expression for induced EMF. My main aim is to write the expression for induced EMF in a coil. Now here I have to write the expression for self-induced EMF. Means I am going to take what? Faraday's law. From Faraday's law, we know that induced EMF E is equal to minus d pi by dt. What? Induced EMF E is equal to minus d pi by dt. Here I am going to substitute the pi value. When I am going to substitute the pi value, what is going to become? D by dt of, in place of pi, what is that? Li d pi, it will be Li means the induced EMF E is equal to L. I am going to take constant. Self inductance will be proportional to constant. No, I am going to take L, it will be outside. E is equal to minus L into di by dt. This is the expression for induced EMF. Yes or no? This is the expression for induced EMF. Clear? Yes or no? We know that pi is directly proportional to I. Pi is equal to L. L only we are going to call it as what? Coefficient of self-induction or self-inductance means E is equal to minus L into di divided by dt. Yes or no? Minus di divided by dt. Here we have to write the unit for self-inductance. No? Yes or no? We have to write the unit for self-inductance. Yes or no? We have to write the unit for self-inductance. The unit for self-inductance, it will be simple. See here, pi is equal to Li. Yes or no? Pi is equal to Li. L means what? Pi by I. L means what? Pi by I. Here L is pi by I means. Yes or no? Pi by I means. What's the unit for magnetic flux? Earlier we discussed Weber. Magnetic flux, it will be Weber per ampere. Current will be what? Ampere. Weber per ampere, or we are going to call it as Henry. The unit for Henry, it will be what? Henry. The symbol, it will be H. Okay. The unit for flux, self-inductance L, it will be L is equal to pi by I. Pi means magnetic flux. Weber, I means current. It will be Weber per ampere, or we are going to call it as simply Henry. Symbol, it will be H. Yes, symbol, it will be H. Same way here we have to write what? Dimension we have to write. We have to write the dimension means it will be simple. Say I am going to work out here. We have to write the dimension. L means what we are going to write dimension. Flux pi means B into A divided by I. Here we don't know the dimension formula for B. B means I am going to write for B F by QE. B means what? F by QE. F is equal to QE. We know Moon charges and magnetism. F means force M1 L1 T power minus 2. Q means charge A power 1 T power 1. Velocity means L power 1 T power minus 1. Yes, L power 1 T power minus 1. I am going to simplify this plus 1 minus 1 is cancel. Means the magnetic field B is equal to M1. This plus 1 comes to the numerator means that will be minus 1. Again plus 1 minus 1 is cancel. L power 0 T power minus 2. This A power plus 1 comes to the numerator means that will be A power minus 1. This is the expression for what? Sorry, this is the dimensional formula for magnetic field. Magnetic field means M1 T power minus 2 A power minus 1. Again this will be area. Area means L square. Length square L square divided by current means A power 1. This A power 1 comes to the numerator means minus 1. Minus 1 minus 1 is going to become minus 2. Therefore, the dimensional formula we can write M1 L power how much? 2. L power 2 T power minus 2 A power minus 2. This is what? Dimensional formula for self-inductance. Simple. The flux change is directly proportional to current. Flux pi is equal to Li. According to Faraday's law, we can write E is equal to minus d pi by dt. Means minus d into Li. L we can take proportionality constant outside the differentiation. Means the minus L into di by dt. The SI unit will be Weber per ampere or Henry. The dimension it will be M1 L square T power minus 2 and A power minus 2. This is the dimensional formula. Now, here in your one mark, they will ask define self-inductance. Define self-inductance or define L. Define self-inductance or define L means definition of L. Definition of L means self-inductance. Definition of L. Okay, we have to write the definition for L. Here we have to write the definition for L means that will be simple. See here in this formula I am going to write L is equal to E divided by di divided by dt. What? L is equal to E divided by di by dt. Here negative sign what? According to Lenz law, this shows what? Opposes the change in magnetic flux. Yes, the motion of the magnet opposes the change in magnetic flux according to Lenz law. I'm going to neglect the negative sign. L is equal to E divided by di by dt. When di by dt, yes, now when di divided by dt is equal to 1 ampere per second, L is equal to what? E. Yes, now L is equal to E. Now we can define the self-inductance. Yes, now we can define the self-inductance. The self-inductance means here, also here, the self-inductance of a coil is equal to induced EMF. Yes, now L is equal to E. The self-inductance of a coil is equal to the induced EMF. Yes, now is equal to the induced EMF when the unit rate of change of current. Yes, now when the unit rate of change of current linked with the coil. Yes, now unit rate of change of current linked with the coil, we are going to call it as what? Self-inductance. Yes, now self-inductance. Yes, sir. Simple one. See here, L is equal to E. Self-inductance of a coil. Self-inductance of a coil is equal to the induced EMF. Self-inductance of a coil is equal to the induced EMF, electromotive force, when the unit rate of change of di by dt, unit rate of change of magnetic flux, unit rate of change of magnetic flux linked with the same coil. Yeah. Yes, sir. Now we have to write the definition for proportionality constant or coefficient of self-induction or self-inductance. L means in this equation what we derive the expression for induced EMF. We can extract L is equal to E divided by di by dt. When di by dt is equal to 1 ampere per second, L is equal to E. So L is equal to E. The self-inductance of a coil is equal to the induced EMF. Self-inductance of a coil is equal to the induced EMF when the unit rate of change, unit rate of change of current. Unit rate of change of current. Unit rate of change of current linked with the same coil. Yes, no, unit rate of change of current linked with the same coil. We are going to call it as what? Self-inductance. Yes, no, self-inductance. Okay, clear? Now in this one, we again one more question they will ask. Define 1 Henry. Yes, no, they will ask. Define 1 Henry or define the SI unit of self-inductance. Okay, define 1 Henry. Definition of 1 Henry or SI unit of define SI unit of self-inductance L. Define SI unit of self-inductance they will ask. Here, yes, define 1 Henry or SI define self-inductance, SI unit of self-inductance. Simple one. Again, the same formula I am going to take. I have to define L now. Means we can write L is equal to E divided by di divided by dt. Here I have to define 1 Henry means L is equal to what? 1. When L is equal to 1, induced EMF E is equal to 1 volt and di by dt is equal to 1 ampere per second. 1 ampere per second. The dI by dt is equal to 1 ampere per second. L is equal to 1 Henry, E is equal to 1 volt, dI by dt is equal to 1 ampere per second. Now we can write the definition. Now we have to say 1 Henry now. The self-inductance of a coil. The self-inductance of a coil is said to be clear. The self-inductance, L means the self-inductance of a coil is said to be 1 Henry. Is said to be 1 Henry if 1 volt of EMF, 1 volt of EMF, electromotive force EMF induced in a coil, EMF induced in a coil, 1 volt of EMF induced in a coil due to dI by dt will be 1 ampere per second, no, due to unit rate of change of current linked with the same coil, linked with it. Okay, unit rate of change of current linked with it or linked with the same coil. Clear? Yes or no? So I will ask define 1 Henry and define SI unit of self-inductance. Means L is going to become 1 Henry. When the L is going to become 1 Henry, E is going to become 1 volt and dI by dt will be 1 ampere per second. 1 by 1 is 1 now. Yes or no? Now we can say the self-inductance L, the self-inductance of a coil is said to be 1 Henry. The EMF induced in a coil, the EMF, 1 volt of EMF induced in a coil due to unit rate of change of current. Yes, no, due to unit rate of change of current with it or linked with it or linked with the same coil. We are going to call this what? Self-inductance. Okay, definition SI unit of self-inductance. Clear? Yes, no, this is about what? Self-induction. SI unit of self-inductance and EMF induced in a self-inductance, SI unit and dimensional formula about self-induction. Clear? So self-induction. Now we can go for the one derivation, 3-mark derivation. We can look into one 3-mark derivation. Derivation. Derive the expression for self-inductance L of a solenoid. Derive the expression for self-inductance L of a solenoid. We have to derive the expression for self-inductance of a solenoid. Here, 3-mark derivation they will ask. Derive the expression for self-inductance of a solenoid they will ask. Simple one. Here, they are asking the derivation test. I am going to write a simple diagram. What I am going to do means I am going to take a solenoid. Long straight wire is going to move in the form of helix. I am going to take a solenoid. This is the solenoid of length L I am going to take. This is the solenoid of length L and capital N with the number of turns. This is capital N with the number of turns. Here I with the current flowing through the solenoid. I am going to take I with the current flowing through the solenoid. This is about what? I am going to take solenoid of length L and capital N with the number of turns and I with the current flowing through the solenoid. Okay. Simple one. Here I am going to take small n, number of turns per unit length. Yes, no, small n I am going to take number of turns per unit length. Means that will be small n is equal to capital N divided by L. Capital N is what? Total number of turns. L is the length and small n is the number of turns per unit length. Number of turns per unit length. Number of turns per unit length. Small n is the number of turns per unit length I am going to put. Okay, this is about your diagram. Say what will happen when the current is going to be flows in the coil, is going to be produces a magnetic field. Already in moving charges and magnetism, we derive the expression for magnetic field inside the solenoid. No? As a moving charges and magnetism, according to Ampere's circuit law, we derive the expression for magnetic field inside the solenoid. Now, the magnetic field inside the solenoid. The magnetic field inside the solenoid, that is P is equal to mu naught Ni. Yes, sir. P is equal to mu naught Ni. I am going to take this is the equation 1. Remember, moving charges and magnetism. According to Ampere's circuit law, we are going to derive the expression for magnetic field inside the solenoid. Okay, when this coil is going to be produced as a magnetic field, what will happen? The flux is going to be changes. Now we can write the flux linked with the coil. Yes, and the total flux linked with the coil. 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 I am going to write flux pi is equal to, already you people know that when a coil having n number of turns, n BA cos theta. Flux pi is equal to what? NBA cos theta. When flux pi is equal to NBA cos theta, here I am going to take angle between B and A, it will be 0. Means both magnetic field and area vector will be acting in same direction. Theta will be 0, cos 0 will be 1. Yes, sir, cos 0 will be 1. Means the flux pi is equal to NBA. Flux pi is equal to NBA. Clear? Yes, sir. Flux pi is equal to NBA. In this equation, I am going to take okay. In flux equation, I am going to substitute capital N value. Flux pi is equal to NBA. Now, N means what? Total number of turns. N means that will be small n into L. Clear? Capital N is equal to what? Small n into L. I am going to write small n into L. B means what? Mu naught Ni. In place of B, I am going to write mu naught Ni. Mu naught Ni. Then last will be what? Area. A means the flux pi is equal to mu naught N into N square L I A. This one I am going to take equation 2. Okay. According to the definition of self-induction, we know that flux pi is equal to Li. Flux is direct, change in flux is directly proportional to current. The proportionality constant we are going to call it as self-inductance. No? Flux pi is equal to Li. This one equation 3. Now I am going to equate equation 2 and 3. Clear? Yes, sir, I am going to equate equation 2 and 3. When I am going to equate equation 2 and 3, Li is equal to what? Mu naught N square L I A. I will be cancelled. The self-inductance of a solenoid, capital L is equal to mu naught N square L A. Mu naught N square L A. Clear? This is self-inductance of a solenoid, mu naught N square L A. Simple derivation, I am going to take a coil of length L and capital N is the number of turns in a coil. Now small n is number of turns per unit length, capital N divided by L. This is capital N divided by L. Now according to the moving charges and magnetism, the magnetic field inside the solenoid B is equal to mu naught Ni. Here is going to, coil is going to produce a magnetic field. What will happen? The flux is going to be changes. The change in flux is given by NBA cos theta. Here area vector and magnetic field, it will be same direction. Theta will be 0, cos 0 will be 1. Flux pi is equal to NBA. Here I am going to write in place of capital N is number of turns per unit length. Now capital N is equal to small n into L. B mu naught Ni area. I am going to get this equation. Now we know that according to definition of self-induction, pi is equal to Li. I am going to equate both the equation. I am going to get L is equal to mu naught N square into La. Now, in this solenoid, inside the solenoid, I am going to place a magnetic material. I am going to place a magnetic material of permeability mu r, relative permeability. Yes, a magnetic material of relative permeability mu r. When I am going to place, what will happen? The L is going to become mu naught mu r n square La. Why means when I am going to place a magnetic material of permeability means what will happen? When I am going to place a magnetic material, here what's the magnetic field strength producing is going to be increases. When magnetic field strength is going to be increases, the self-inductance is also going to be increases. Okay, so self-inductance is also going to be increases. Clear? The self-inductance L is equal to mu naught mu r n square La, because we know that mu r relative permeability mu r is equal to mu by mu naught. When I am going to place a magnetic material, mu naught for free space, any medium is mu naught. Mu in place of mu, we can write mu r into mu naught. Yes, mu r into mu naught. Okay, this is about what? Self-inductance of a solenoid. Yes, self-inductance of a solenoid. Clear? Thank you.